Pleasure to have Bhuwan Dhingra from CMU. He's a final year PhD student and he works with Professor William Cohen and Ruslan Salakino. So his research uses natural language processing and machine learning to build interface between AI applications and world knowledge facts. His PhD is supported by the Siemens Future Makers Fellowship, and prior to joining CMU, he did his undergrad from IIT Kanpur, India, and he spent 2 years at Qualcomm Research in the beautiful city of San Diego. Right? Let's welcome Bhuwan.
Thank you, Rajshi. So, thanks everyone for coming today. I'm going to talk about some of the work I've been doing over the last year on treating text corpora as knowledge bases. So, most of my work looks at the task of factoid question answering, where given a natural language question, like who was playing in Family Guy, we want to find the answers to that question, in this case, Myla Kunis and Lacey Jabber. And by factoid here, what I mean really is that the questions are all about relatively straightforward facts, the kind of things that most of us would agree on the answers to, and which are usually, about names of places, people, things, dates, and short answers like that. Now, whenever you're looking to build a factoid question answering system, one of the key considerations that you must first think about is what is the source of information? Where are you actually going to look for answers to the questions that you want to be able to answer? And two sort of main sources of information that people have looked at a lot are text corpora and structured knowledge bases. So text corpora includes things like Wikipedia, news articles from Reuters or Reddit or Twitter, and these are the kind sort of things that you and I would look for answers to the questions that we have, right? On the other hand, we have structured knowledge bases, where information is organized in a more, it's stored in a more organized way, according to some predefined format. And I'm going to talk a little bit more about that, but some examples include Freebase is a very large knowledge base, so, and Wikidata. So if you go on the Wikipedia page, you click, there's a link on the side called Wikidata item, which lists out some properties about the entity whose page that's about. And that's really another source of information that you can think about for using to answer questions. A lot of prior work has looked at either or one of these sources of information and using them for the task of question answering itself, and they really offer some complementary benefits. On the text side, so as I said, text corpora are written in natural language, and natural language is very expressive. Anything, any piece of information that you can think of, you can usually write it down in a sentence, but you may not be able to populate a database with that information. So text is really high recall. It captures a lot of varied kinds of information. Knowledge bases, on the other hand, are built according to very fixed rules or a fixed format. And knowledge bases are built more for computers, for us to be able to write computer programs to efficiently manipulate the information inside the knowledge base. For that reason, I'm going to call it a high precision store of information, because not everything is expressible in that, but the things which you can express in databases, it's usually easier to write computer programs to manipulate that information. The other big difference that I would say between these two is that text, corpora, they are in natural language, and question answering, the questions are also in natural language. So you have this lexical overlap, which is a really strong signal when you're looking for answers to questions from a text corpus. On the other hand, databases or knowledge bases, because of their fixed format, they allow reasoning procedures. And I'm going to come to this detail. I'm going to talk about what kind of reasoning procedures are easy in a bit. But really the motivation of this talk and a lot of my work is how can we combine these benefits, that these complementary benefits that text and knowledge bases provide. So on one hand, can we take knowledge bases and add more information to a knowledge base by using text? And on the other hand, can we take a text corpus and use a knowledge base to be able to do reasoning procedures over the information that is there in a text corpus? And at this intersection, there is some work, and a lot of it is from UMass Amherst, from Andrew's group on universal schema. In particular, the work that I'm going to describe today is really focused on end-to-end question answering, and there is one baseline which I'm going to talk about later. Okay, so I've talked about some of the motivation why we want to consider a combination of text and knowledge bases as a source of information. I'm now going to dive into two specific projects from the last 1.5 years. In the first one, I'm going to talk about how we can use a text corpus to add information to an incomplete knowledge base and use that for question answering. In the second part of the talk, I'm going to flip the problem and I'm going to talk about how we can use the structure provided by a knowledge base to do reasoning over a text corpus. Okay, so going into the first paper, which was published at MLFL last year. This was joint work with Hai-Chin Sun, a master's student at CNU. Okay, so I've been talking about knowledge bases, but let me define a little more clearly what I mean by that. There are many different types of knowledge bases, and the ones that I'm going to focus on here, and which a lot of the NLP community has also focused on, are what I call entity relation knowledge bases. These are really a large collection of facts, where each fact expresses a relation between a subject entity and an object entity. And one way to visualize these knowledge bases is in the form of a graph, as is shown here, where the nodes of the graph represent real-world entities. For example, the show Family Guy, or the character in that show Meg Griffin. And the edges between these nodes represent relations between those entities. Now, relations are typically unidirectional. So Family Guy has the character Meg Griffin, but for each relation we can also think of an inverse, so that's why I'm showing a bidirectional edge between those nodes. The special thing about these kind of knowledge bases is that they organize information around entities. So all the information about Family Guy is really in this neighborhood around the node which represents Family Guy, which is really one of the key features of knowledge bases, which allow you to do reasoning over it. Through a combination of hand curation and information extraction methods, there are some very large publicly available knowledge bases. One example that I'm going to use a lot is Freebase, which has about 44 million entities and more than 2 billion facts. So it captures a lot of real-world information. Now, I've been also talking about reasoning in knowledge bases. There are many different things that you can do with a knowledge base, but one operation which is particularly easy to implement and is useful for a lot of different tasks is what I'm going to call the relation following operation. So starting from a set of entities X, you can follow all edges, all outgoing edges labeled with a particular relation R to arrive at an output set of entities Y. And I'm going to denote this by x.follow R. This is very easy to implement against a structured knowledge base in a very efficient manner. So for example, if you have the starting set Family Guy and that's empty show, you can follow the network edge to arrive at the singleton set, which is Fox. Once you have this operation, it turns out it's also really useful for answering a lot of different types of questions. So for example, if you go back to the question I showed at the beginning, which is who voiced Meg in Family Guy, one way to go about answering this question is to identify the entities in the question, in this case Meg and Family Guy, and then find a program or a parse of the question which uses the relation following operation that I just described to denote the answer in some form. So for example, here you can think of the answer as being the output of this operation, where you start from Meg Griffin and you follow the voiced by H. And in general, this is a simple example. You can define more complicated programs given a question. And once you execute this operation against the knowledge base, you arrive at the two answers. Now, of course, the challenging part here is to figure out, given a natural language question, what that intermediate program looks like, which you can execute against a knowledge base to find the answer. And really, one way which people have looked at a lot is to go out, collect a bunch of questions, annotate their semantic parsers or such programs, and then train a machine learning system to identify the program for a new question. But annotating such semantic parsers is pretty expensive. So a lot of work has looked at this setting called learning from denotations, where you don't know the intermediate program, you just know the question and its answers, and you must search for the intermediate programs which lead to the correct answers during training. And this is really the setting that I'm also going to focus on. Another issue with knowledge bases, which I've discussed a little bit, is that they are heavily incomplete. So incompleteness comes from two sources. One is that a lot of information is just not expressible in the format that knowledge bases support. But even the kind of information which can be populated in a knowledge base, real-world knowledge bases are highly incomplete. They don't actually store all that information. So, for example, this study from NACL 2013 shows that freebase, around 90% of relations about people are missing from freebase. And really this incompleteness adds to the difficulty of that learning from denotations setup that I just discussed. Because if you have a question and its answers, but the knowledge base is missing the relevant links which go from the question to the answer, the search problem becomes even more difficult. So the goal of this project was to see if we can complete knowledge bases using text. And to do that, I'm going to describe an approach which takes the existing knowledge graph that we had, and it augments it with textual sentences from a corpus. And in this case, the corpus is going to be Wikipedia. So how are we going to do that? Well, we start with the question, and we identify relevant text for that question. For this, we use a standard information retrieval pipeline based on TF-IDF features. And then the top n sentences, I think we used 50 in this case, that are retrieved from Wikipedia using this question as the query. We go and we create a node in the graph for each of the text sentences that we retrieved. And we connect it to the rest of the graph using entity linking. So we identify spans within these text sentences which refer to an entity within the graph, and we use an off-the-shelf entity linking system for this purpose. And we connect them to those nodes using this special new relation called links2, which is really just a general relation. So now notice that even if the original graph had an edge missing between Family Guy and Meg Griffin, we still have a relatively short path linking those two entities, which talks about the fact that Meg Griffin was a character from the TV series Family Guy. So using this retrieval process, we now have a more complete graph, which does talk about a lot more information. But the other part was, how do we search for paths within the graph which are relevant to our question, or which lead to answers to our question. And now that problem is more complicated now, because we don't have like these fixed set of relations connecting our nodes. Now we have these new textual nodes in the between, which sometimes connect entity nodes. And now when we search for paths which lead to the answer to the question, we must also search through these textual nodes.
So these are textual nodes or textual edges, like which forms relation?
No, these are textual nodes, The edges, as I said, are all sort of uniform edges, but these are extra nodes by themselves.
So that entire text blob represents Meg?
Yeah, but the edges actually don't go from the whole node to an entity node, they go from a span within that node to the entity node.
Oh, I see.
So it's really it's a special kind of an edge,
Right.
which doesn't link the whole node. There's information about the span within the node which links to the entity, and that's going to be relevant because otherwise there would be no way of differentiating Meg Griffin from Family Guy within this node. Okay, so now the other part of the problem is to search for the paths which lead to the correct answer given a question. And for this, we're going to use some form of representation learning. In particular, I'm going to discuss a method which uses graph neural networks to learn embedding vector for each node and each token in my textual node, such that that embedding vector captures the path information in a small neighborhood around those nodes. And we're going to use those embedding vectors to find answers to our questions. Now, those of you who don't know, graph neural networks are these general neural network architectures used for learning representations of the nodes within a graph based on the neighboring nodes around those nodes that we're learning the representations for. And one additional sort of feature we're going to add to our graph neural network representation is, now the problem with standard graph neural networks is that they treat the whole graph as a homogeneous graph. There's really no notion of certain nodes being more important than other nodes. And for our question answering problem, that's pretty important. Like, given the question, who was Meg in Family Guy, I know that the answer to this question is in some neighborhood around the entities which are actually mentioned in the question, in this case Meg and Family Guy. So in order to build in that inductive bias into our graph neural network model, I'm going to introduce what I'm going to call a PageRank score for each node in the graph, which is really just a scalar score associated with each node. And initially, I'm going to start by making it uniform across the entities which are mentioned in my question. So in this case, Meg, Griffin, and Family Guy. Okay. Then the general procedure for a graph neural network is something like this. We initially assign some embeddings to each node. And then across some t iterations, we update the embedding for each node. And the updates depend on, in our case, they're going to depend on three different things. So the first thing is going to be a self-connection. So it's the embedding of that node from the previous time step. The second thing is going to be the entity neighbors of that node. So in this case, for example, Meg Griffin, the update is going to depend on its neighbors Myelactunus and Basic Javert and Family Guy, and and there's like a special weight associated to the update coming in from each of its neighbors, and that weight is going to depend on the question itself. And then the third thing, because we have now a heterogeneous graph, we have both entity nodes and textual nodes. We added a third term in this update equation, which depends on the textual mentions of that entity node. So in this case, the Meg Griffin mentioned within this text node. And we're going to repeat this for t time steps. And really the number of iterations we use here, the capital T, decides how far in the graph are we willing to consider to look for answers. Now, as I said, the general graph network formulation, there is no notion of certain nodes being more important than others. And that's problematic because really we know that for our question answering problem, what we're looking for is paths. A path starting from either Family Guy or Meg Griffin, which is mentioned in the question, and taking a few steps starting from these nodes to arrive at the answer. So to build in that sort of a bias into the propagation process here, what we do is we use the PageRank scores that I defined in the previous slide. So, and what we do is pretty simple. So at each time step, we only propagate out from the nodes which have a non-zero PageRank score. So in the first time step, what that means is we're going to only propagate embeddings from Family Guy and McGriffin. And at the same time, we're also going to update the PageRank score associated with each node. So that's going to look like a pretty standard personalized PageRank formulation for those of you who are familiar with that. So after time step 1, we have some weight on the neighbors of Family Guy and McGriffin, in this case Myla Kunis and Lacey Chabert. And then in the next time step, we're going to further propagate outwards from these nodes to their neighbors. And the reason why this is helpful is, like in general, let's say this is our answer. In general, if you use a graph neural network to learn the representation of this, that is not constrained in any way. So information might be coming in from any of its neighbors. And we found that that sort of formulation leads to overfitting because there's no sort of bias which says that, okay, there's, what we're looking for is a path from the nodes in the question to the answer nodes. And then finally, once we have, after some steps of propagation, once we have final node representations for each of our nodes, we pass a neural network encoder function through our question itself and match the representation of the question to the representation of each of the nodes to classify each entity as being an answer or a no answer. So we assume that there may be multiple answers for a particular question. So to summarize, we started off with the goal of answering questions against a knowledge base, but the knowledge base might be incomplete. So we used a TF-IDF-based retrieval mechanism to inject text into the knowledge base. Then we propagate embeddings around nodes starting from the entities which are mentioned in the question. And finally, we classify each entity as being an answer or a no answer.
I'm still trying to understand what PageRank does in your process. So it kind of determines.
So PageRank basically acts as a weight on this second term. Whenever I'm updating the embedding of a node, I'm only going to accept an update from nodes which have a non-zero PageRank score. So what that does is, let's say Myla Kunis also acted in that 70s show.
Sure.
But that is not at all relevant to the question I have here. So it blocks off updates which are not relevant to the question I have here. And really, the cases where it helps is if you have very little training data, it helps match the path which links the entity in the question to the answer better to the natural language expressed in the question. And it prevents it from overfitting to paths which are not relevant to that question.
I see. So the PageRank is per question for the nodes?
Yeah, it's dependent on the question because we link the entities in the question and that's where our PageRank starts. So it's a personalized PageRank process actually. Yeah.
How many steps are you running PageRank for?
So that's the same number as the graph because every time we update the embeddings of a node, we also update the PageRank scores of that node. And in this case, we went up to 3 steps.
Maybe you're going to get to this, but how does it work at inference time with the personalized PageRank if you have a new question?
So we run an entity linking system over that new question, and we do the exact same thing. We start with the PageRank score uniformly distributed over the entities identified in the question, and then we propagate out from that. So it works exactly the same during training or inference. Yeah. And actually, the PageRank, one other benefit it provides is I know now that I really only need to look at a neighborhood around the entities in the question. So it helps to, in pre-processing itself, we can throw away much of the graph, and it helps to fit inside, say, one GPU.
So I'm not following how you choose which edges are weighted more for information.
Yeah. So I sort of skipped over that detail, but that's based on these learned weights. which matched some relation embedding of these edges to the natural language question.
So it is question
It is
specific.
question dependent. The PageRank propagation is also question dependent. The initial nodes that you start from is also question dependent.
So that seems pretty crucial. If we could hear more in detail about that.
I don't have slides on that, but basically the idea is we have some encoder function over the question, and we match that to a relation embedding here, which is learned end to end on the supervised tutor class.
One thing that comes to mind is you could imagine that an edge in and of itself may not seem that relevant, but in the context of a little chain taken between two different points in the graph, it could be very relevant.
That's true. And that's very related to some of the failure cases that I'm going to describe pretty soon. Basically, there are certain constraints. So often you want to know the constraint that Medicube voiced in 1999 versus Lacey Chilwell voiced it in 1998. And really, for certain questions, those constraints become really important. But the PageRank process actually makes it harder to learn about those constraints. And that's definitely a limitation over here. Okay, so for evaluation, we looked at two data sets. First one is called Web Questions SP, which is really open domain questions about, for example, languages, heads of governments, and stuff like that, factual questions. Here the knowledge base was all of Freebase, and the text corpus was all of Wikipedia. And we had about 5,000 question answer pairs for training, so it's a relatively low resource setting. The other data set we looked at was Wiki Movies, which are questions about movies, like which movies did Quentin Tarantino direct. And here we had smaller TB, which is a subset of the Open Movies database. It had only about 8 relations, whereas the web questions setting had, Freebase has some, I think, order of 1,000 relations. And the text also here is some 17,000 introductory paragraphs from Wikipedia. And here we had about 10,000 question answer pairs for training. Now the important thing is that both these data sets actually are completely answerable using just the knowledge base part. So we do know the sort of the upper bound if you have a complete knowledge base, how well we can answer those questions, but we also simulated an incomplete knowledge base setting by just randomly dropping edges from that knowledge base. And sort of the main baseline here is an approach from Rajarshi sitting right here, which uses universal schema representation for jointly taking facts from a knowledge base and textual sentences between entities and projecting them to a common space. And then it learns a memory network style approach to select between the different facts or text sentences to answer the questions. Now, I'm not going to go into much details, but sort of the main difference between what we're doing and what this does is it doesn't really explicitly use the graph structure between different facts and different text sentences when trying to answer the question. That's sort of the main difference here. So I'm going to present the hit set 1 performance, which measures how many cases the topmost answer predicted by the system is correct or not. But remember, in general, a question can have multiple answers, so this is one metric we're measuring. And as I said, prior work has looked at both. So I'm going to talk about 3 different settings here. On one hand, we have no knowledge base, so we just have text sentences. So this is a text-only setting, except that we do have entity links within those texts. And on the other hand, we have a 100% KB setting where we have a complete knowledge base, and we also have text added on to that complete knowledge base. And in the middle is sort of the interesting setting where we have an incomplete knowledge base. And prior work has looked at both the text-only version and the KB-only version for this problem, and there is some established state-of-the-art there. We can take a look at the universal schema-based approach. And we can look at a version of the model that I presented which does not use text, so it just uses the incomplete knowledge base. Of course, it doesn't have any performance in the text-only case. And we can take a look at a version of our model which adds on text to the knowledge base. So a few things to note here. First of all, adding text on top of the incomplete knowledge base has a significant effect, so that's good. That's what we expected. We can also see that compared to the universal schema approach, using the graph structure, using the graph neural network based approach leads to a significant improvement. And in general, it's in the text only versus KB only settings we're comparable to the previous state of the art. The trends for the web questions SP dataset were pretty similar. One difference here was that the universal schema approach actually was worse than the KB only approach, showing that for this dataset the knowledge-based structure is even more important. And there is, like in this case, we found that we were significantly worse than the state-of-the-art, which was built just for a KD-specific approach. And looking at the cases where we went wrong, so first of all, I talked about the PageRank propagation. That was crucial to making this thing work, because as I said, without that, we just had about 5,000, 10,000 question answer pairs here, and there was a lot of overfitting. If you took a look at the errors, so around part of the errors were because of the retrieval part. So, and the retrieval consists of two things. One is, given a question, we need to identify the entities within that question, because that's where we will do our propagation. And entity linking is not perfect. There is error associated with that. And the other part of the error was, given a question, we were retrieving sentences using an information retrieval pipeline, and that also had some recall. So in around 90% of the cases, we found that the answer was, in around 10% of the cases, found that the answer wasn't even there in the neighborhood which we were propagating embeddings in. And then the other big source of error was these constraint-based questions, like who first voiced Megan Family God, which club did Cristiano Ronaldo play for in 2007. Now here, actually the way this information is represented in our knowledge base is through these special nodes. So usually if you have the voice migration between Meg Griffin and Mila Kunis, instead of having a direct edge, the way Freebase represents this information is making it like two steps, where there's this intermediate node which doesn't really represent anything, but is there to link information, like the fact that the starting of this relation was in 99 and the ending was in 2019, and information like that. Now, for the graph neural network based approach, and especially once we add that PageRank based constraint to the propagation, these kind of cases are very hard. Because to get the information from 1999 to Mila Kunis, the number of steps we need to take increases by a lot. We start with Meg Griffin, we come here, then we need to go back to go upwards to 1999, then come back here, and then come to Mila Kunis. So the number of steps that we would need to take would be much larger. And in general, we found that increasing the number of steps did not help with these sort of questions. Yeah.
Could that be due to additionally the bias of PageRank not having seen this information, so these are very contextual,
Yeah.
and so your training data is not diverse enough to give enough weight to these other
so
nodes.
in general, I think if we had lots and lots more data, getting rid of PageRank altogether and propagating throughout the graph would be better. That's true. So that concludes the first part of the talk. So if there are questions, I'm going to take them now.
Can you give us more intuition about where and why it equal charges method?
As I said, so one of the limitations of that method was really it treated the combination of text and facts. Like this is the universal schema representation, but the way it was actually used was there were embeddings learned for each mention of each embedding. So it was represented as a long table, where each entry in that table was either a fact or a text sentence, right? Now, when you want to do question answering, the way you would do that is you do an attention mechanism over that long table. An attention mechanism, it really just sums over all of them. There is no explicit way for it to jump from one fact to another, like if you go from a subject relation object to a different fact where the subject is the object of the first fact. So it loses that sort of an information. And the other thing we found was that there was a big difference between the F1 scores of our method and the baseline method, and a smaller difference between the hit set 1 score. And the reason there was that the attention mechanism aggregates over all facts. So questions where you have multiple answers, those were affected pretty badly. Okay, so now I'm going to jump to the second part of the talk, which is pretty recent work. It's still under review, where I'm going to talk about differential reasoning over a virtual knowledge base. And really the high-level goal here was to use the knowledge base structure to do some multi-hop reasoning over text. So for this part, I'm going to focus on more complex questions, specifically multi-hop questions. So what are multi-hop questions? So for example, if you have something like which TV networks has MLFL appeared on, now the program or the parts for this question that I need to figure out to be able to answer it against the knowledge base looks something like this. So either we start in MLFL, follow the start in relation, followed by the network relation. So there are two applications of that relation following operation. Or I take another path which goes to voiced, has character, network to arrive at the answer, and then I take some sort of a union between the two. So in general, multi-hop questions are questions where you need to piece together multiple pieces of information to arrive at the answer. And the goal of this project was to do this sort of multi-hop reasoning, but over a text corpus and not knowledge base. So how would that look like? So given the same question, which TV networks has MLFL appeared on, if you go look at the Wikipedia pages of the relevant entities involved, we find that in one page we find a sentence like, she voiced Meg Griffin in the series Family Guy, and in a completely different page we'll find a sentence which says that Family Guy was actually broadcast on Fox. So the challenge here is, of course, that the relevant information is now not all around the same entity. It's spread out across different documents. And really that's the assumption that I'm going to work under, that the kind of questions we're trying to answer, the relevant information is spread out across multiple documents. I'm going to talk about this Meta QA benchmark, which is really an extension of the Wiki Movies data set to 2-hop and 3-hop questions. So you have questions like what 1-hop question is the same as what I showed in the previous part, which was what movies did Quentin Tarantino direct. But now you also have questions like which movies have the same director as that of Pulp Fiction, or who acted in the movies which have the same director as Pulp Fiction. Now these are a bit contrived, but the key thing here is that to answer these sort of questions you need to aggregate information from multiple passages. We can apply the graph network-based approach that I described in the previous part to this problem now. And we can again study the hit set 1 performance. And what we found was that if we use the KB and we use the graph network-based approach, there is some drop in performance, but it's not too severe. Whereas if you use text, there is a very severe drop in performance using graph networks. And really the problem here is the retrieval part. So as I said, before we applied a graph network based approach, we needed to take the question and retrieve the top matching passages which are likely to contain the answer. Now notice here the question itself has very little overlap with the second sentence that we need to answer that question. So in general, for multi-hop questions, one of the big challenges is finding the relevant set of passages which you pass on to some neural network model for extracting the answer. And Now, so shallow information retrieval doesn't really work that well here. One option is, so the IR community has actually looked at this problem, and one option is to use something like pseudo-relevance feedback, where you first retrieve an initial set of documents, identify the salient terms within that, and then go back out and retrieve a second set of documents around those salient terms. But what ends up happening there is that you end up with a very large pool of documents from which you need to extract the answer, and in general that becomes expensive pretty quickly. So our goal here was to do multi-hop QA over a corpus, but in an efficient, keeping the inference time fast. So the approach I'm going to describe now consists of two stages. In the first stage, we take the text corpus, we identify entity mentions within the text corpus, and we identify mentions which really talk about the same entity, and we convert this text corpus into something that I'm going to call a virtual knowledge base. And this part really is offline. We're going to do this once in a question-independent manner, and this can be as slow as we like. This can be slow. Then in the second part, I'm going to discuss soft implementation of the relation following operation, which operates over this virtual knowledge base that we constructed using our text. And once we have an implementation of this operation, to answer complex questions, multi-hop questions, what I'm going to describe is a way to cascade them, but still allow learning end-to-end over the question. And we want this second part, which is the reasoning part over the knowledge base, to be fast, because it's going to be online. It's going to happen once we get the question. So what do I mean by the virtual knowledge base? So given the text corpus, what we do is we run an entity linking system once again to identify all the entity mentions within that corpus, which look like something like this, family guy, along with the context in which those entity mentions appear. And then next we are going to define a contextual representation for each entity mention within our corpus. And that representation is going to consist of two parts. The first part is a sparse vector, which is nothing but a bag of words representation around that entity. So it really encodes information about the words or the other entities which appear in the context around an entity mention. And this part is fixed. The second part is going to be a dense vector, which is going to come from a pre-trained model, which is based on BERT with a different pre-training strategy. And note here that these are entity mentions. So the same entity, like family guy, can have many, many different mentions, and each of them will have its own separate contextual representation. So how do we get the dense part? Well, the goal for this dense vector for each mention is to capture the relational information around that mention. So if I have a sentence like, let's see, if I have a sentence like Pulp Fiction is a 1994 film written and directed by Quentin Tarantino, I want the dense vector associated with Pulp Fiction to capture the relations it enters into with these other entities. Like it was directed by Quentin Tarantino, or it was released in 1994. So to encourage these kind of representations, we basically took neural network encoder model over the text. In this case, we started with the BERT model, and we aligned these text sentences with facts from an existing knowledge base. We used distance supervision for this part. And then we trained the model to produce a representation which matches the subject and object, the subject and relation here, which is Quentin Tarantino and directed. So really the goal here is to convert entity mentions into a contextual representation which captures relational information. And this style of pre-training really helps a lot because pre-trained BERT doesn't capture much of this information. Okay, so now once we have the sparse and dense components for each entity mentioned, we are actually going to throw away the underlying text corpus, and this is going to be our only source of information. So now the second part is, given a multi-hop question, how do we do the relation following operation that I had described? So for this, I'm going to introduce an implementation of this, which is soft in the sense that it doesn't require these explicit sets of entities or an explicit relation. It really works, it infers these entities and relation from a natural language question. So the input to this operation is going to be a weighted set of entities, where the weights are going to represent confidence associated with each entity. So for example, this might come from an entity linking system. And instead of explicit relation in a knowledge base, we're going to input a relation vector, which might come from an encoder function, for example, defined over a natural language question. And the way it's going to work is by retrieving spans, retrieving mentions from our virtual knowledge base, which match this condition, that they're related to one of the input set of entities by the relation specified here. And the output is going to be another weighted set of entities. So now, as I said, given a question now, we can run an entity linking system to find VX1. We can use a transformer or an LSTM network to find QR1. And for multi-hop questions, we're simply going to chain these operations one after the other until we arrive at the answer. Now the key idea behind this whole work is that we can implement this operation against this kind of a knowledge base using just a maximum inner product search and some sparse matrix vector products. And what that implies is that this is differentiable. Differentiable in the sense that the weights of the entities here are differentiable with respect to the weights of the entities there. Which means that given a question and its answers, we can backpropagate all the way through to learn the parameters associated with A, finding these relation vectors, and B, the internal parameters to that operation. Yeah.
So the QR2, where do you get that? Is it the same?
So these are two different encoder functions over the question.
And like, so that is encoded based on like VX2? Like, so how is QR2 different from QR1?
No, so these are two different encoder functions, and they're learned separately during training, right? So it's like figuring out a semantic parse of the question. It does not depend on VX2. It's just that, okay, relation 1 is going to be the show that molecules appear, and relation 2 is going to be the network of that show. So it doesn't depend on what the actual show molecules appear.
How do you determine at test time how many such encoders you need?
Yeah, so that there's two options. We did different things for different data sets. In some cases, when you know that it's a 2-hop or a 3-hop question, you can just define those many, or you can define a chain of that many operations. In certain cases, you don't know that, and for that, what we did was we instantiated multiple templates. So we had a 1-hop template, a 2-hop template, a 3-hop template, and in the end, the final answer was a weighted average across all those. So it's like you're learning to answer a question using different templates, and you're learning a classifier which selects among those templates. Okay, so I'm going to quickly run through the actual implementation of this follow operation against this kind of a knowledge base. So as I said, the first thing we derived from our natural language question is a weighted set of entities which we represented as a k-sparse vector over all possible entities. So this is a vector whose size is the same as the number of entities, but it has only at most k non-zero entries. So this can come from an entity linking system. And the non-zero entries of this k-sparse vector are the weights or the confidence associated with each entity. The second part is a relation vector, for which we used a 5-layer transformer network over that question. And now given this set of entities and this implicit relation represented by that vector, we want to retrieve the mentions from our knowledge base which satisfy this relationship. And for that we proceed in 2 steps. So the first step takes the entities detected in our question and it computes an average TF-IDF vector based on the surface form of those entities. And we match that using an inner product to the sparse component of each mention in our knowledge base. So at a high level, what this means is that I'm basically looking for mentions in my knowledge base which co-occur with one of the entities that are detected in my question. And the cool thing here is that the TF-IDF vector for each entity is fixed. The sparse component for each mention is also fixed. So we can pre-compute this operation which matches an entity to one of the mentions in my knowledge base. We can pre-compute this whole thing into one big sparse matrix. And then online, once we get the question, all we need to do is we need to multiply the sparse vector above with this sparse matrix here, which can be implemented pretty efficiently. And yeah, so the complexity of this whole operation does not depend on the number of entities or the number of mentions. It just depends on the number of non-zero mentions per entity. Then the second part matches the dense component. So we have a dense relation vector here, and we want to match it to the dense component of our mentions in the knowledge base. And for that, we use the maximum inner product search to identify the relevant mentions. And then eventually, finally, we retrieve only those mentions from the knowledge base which match highly with both these components. So it's like a intersection of those 2 retrievals. And again, at a high level, the sparse component is there to see that, okay, which mentions co-occur with some of these entities. And the dense component is there to see, okay, which of them fit the correct type or the correct relation requested by the question. And then lastly, remember that these are mentions. So there may be repetitions. The same entity might be mentioned multiple times here. Whereas what we want at the output of our operation is a set of entities. So we use co-reference information, which tells us which mentions refer to the same entity, and we aggregate them to an output sparse vector here, which I'm going to call bx2. And then for the second hop within our question, so I'm assuming here I know that this is a 2-hop question. For the second hop, we're going to derive the similar second vector and apply the same operation again. So so to summarize, this is what the whole operation looks like. And I'm not going to go into the details here, but the thing to note here is that every operation is either a multiplication, either a vector matrix multiplication or an element-wise multiplication or a maximum inner product search, and all of this is differential. So what that means is that the weights of the output entities are differentiable with respect to the weights of the input entities and that relation vector. So we can learn end-to-end given just the answers and the question. And it's efficient because every operation it depends even only on the log of the number of entities on the page. Okay, we can go back to the Medicube dataset that I described at the beginning. And we can again look at the headset 1 performance now against just text. So the source of information is just a text corpus. But these questions are answerable against a knowledge base. So we have some state-of-the-art performance if you were to use a knowledge base. And the previous best for this benchmark is this paper which was published at MLFL this year called PageRank. And for our approach, we compared 2 different approaches. So one of them is an end-to-end approach, where we're just given the question and its final answer, and we know how many hops of reasoning do we need to run. The other approach that we compared to was where we do know the intermediate answers that the system was putting. So if you have something like which other movies did the director of Pulp Fiction direct, so we know that the intermediate entity is Quentin Tarantino, and we can add that supervision to our pipeline. And it's worth noting that PullNet actually does have this kind of a supervision. So we found that in our case, actually using or not using the supervision did not make much of a difference. The system was able to learn completely end-to-end. And I've been talking a lot about efficiency and runtime. So we also found that our method was much faster than PullNet.
Sure.
And really, PullNet does something similar to a pseudo-relevance feedback thing, where it first retrieves an initial set of documents, runs a graph neural network over them, and then it retrieves a second set of documents and runs a graph neural network again. We also tried on the more popular Hotpot QA benchmark. Now, our system really assumes that the answers are entities. So it's not directly applicable to this Hotpot QA task, but there is a subtask of the Hotpot QA benchmark where it is applicable. So for those of you who don't know, Hotpot QA is another multi-hop QA task where given a question, there are two relevant paragraphs and certain relevant sentences within them, and the answer can be any arbitrary span within these two paragraphs.
But the answer here is an entity, right? Property is an entity.
Yeah, so for like 70% of the cases in Hotpot, the answers are entities, but there's also a significant chunk where the answers are not entities. And we looked at the subtask of Hotpot where given the question, we just need to identify the two paragraphs which contain the answer to that. And because these are Wikipedia paragraphs, they're the first paragraph from a Wikipedia page, each paragraph is really associated with an entity. So the task that we were looking at was, given a question, identify the two entities whose paragraphs would contain the answer to that question. And this is a much larger study, so we have about 5 million entities, around 22 million mentions, so our virtual knowledge base was 22 million entries, and it ended up being the size of about 34 gigabytes. So yeah, I'm going to talk about the accuracy at K metric over here, which is the number of cases where the top K entities retrieved by our system contain the two bold entities which are required to answer the question. And the baseline is again a paper from UMass this year and from the UMass Amherst, which does some iterative retrieve plus read sort of an approach. And we found that we got better results than that. But more importantly, we found that our approach was about more than 10x faster than the baseline, which did an iterative retrieve plus read sort of a pipeline. Okay, one other thing I would like to point out here is that using these sort of templates and like an explicit relation following operation, one benefit here is that we produce actual answers to intermediate questions. So if we take a look at the sparse vector produced by one application of the relation following operation, these can be considered as predictions to the intermediate question. Right? So there's some amount of interpretability here. So you can ask the question, what do those predictions look like? So we inspected some 100 correctly answered two-hop questions from the MetaQA benchmark. And we found that around 83% of them did have at least one correct answer in the intermediate predictions. And in 80% of those, that prediction was the topmost answer. But the more interesting thing here is what happened in the other 17% of the cases. How can a model make a final prediction as correct when it did not get the intermediate prediction as correct? And in fact, in these cases, we found that the model learned to cheat. So if you have a question like, what are the genres of the films directed by Justin Simien? This can be thought of as a two-hop question, but it can also be answered directly by hopping from the director to the genre, because that information is there in the same passage. So in this case, the model just learned to answer the question in one hop and copy over that answer to the second hop. So that's it for the second part as well. To conclude, Lil, I just want to sort of throw out this idea that I've been thinking about, that word embeddings were hugely popular across NLP tasks, where you take all the words in your vocabulary, you learn some fixed size vector for it, which is sort of captures the global knowledge about that word that you have, and then you inject it into downstream models. So now the question is, can we take mention embeddings or span embeddings or contextual embeddings of a whole corpus? So for example, what if I take all of Wikipedia and I contextually encode... So we still have some room to work on question answering. But yeah, what if we just take all of Wikipedia, we contextually encode every entry mentioned in that? Now, this kind of knowledge, what other tasks can it be useful to? How can we inject this knowledge into downstream NLP tasks, and where all can it be useful? That's sort of the general direction that this work is headed towards. Thank you.